Hello, everyone. Welcome to the webinar. My name is Brad Harrison, and today we're going to talk about streaming potential and its use of capillary electrophoresis analysis for both fundamental research and routine analysis. Our speaker is Dr. Vadim Okun. He has a PhD in analytical biochemistry and works for Lumex Instruments as a project manager. He's responsible for the development and promotion of capillary electrophoresis instruments and related analytical applications for food and beverages, ecological analysis, and biopharma. But before we start, let me talk about the feedback possibilities. On the bottom of your screen, you can see the Q&A panel. Please enter your questions in this area. We'll try to respond as much as we can after the presentation, and all unanswered questions will be answered by email after the webinar. Now I'd like to give the floor to Dr. Vadim Okun.
So thank you very much, Brad, for this very kind introduction. Good morning, or probably good afternoon, ladies and gentlemen, for this webinar. Today I would like to talk about a very interesting, at least to my mind, a very interesting and perspective feature of our capillary electrophoresis system Capel, which is currently manufactured by Lumex Instruments. This is streaming potential and its measurement. So the title of today's talk is New Perspectives in Performing Long Series of Capillary Electrophoresis Analysis using Streaming Potential Control. In the talk, I will shortly introduce you our company Lumex Instruments. Then I would like to underline why we actually propose to control streaming potential, stay on some details how it was implemented into the hardware and the software design of the instrument, and finally we'll demonstrate on some certain examples how it works and thus who could be actually interested in getting instruments with such an interesting option. But let me first introduce you our company Lumex Instruments. It's a worldwide known as a company which manufactures analytical instruments and develops the necessary analytical protocols to be realized on them. We have more than 20 types of product lines for academic and industrial research, process and environmental control, and of course also for the QC departments, for the quality control, starting from the life sciences through waste management, food testing, agriculture, and up to pharmaceuticals, including biopharmaceuticals. Our headquarters is located in Vancouver in Canada. We have an important production facilities and research center in St. Petersburg, Russia, and several sales offices in Europe, just only Hamburg in Germany, and Beijing, China. So about 350 highly skilled employees are working on Lumex worldwide, and we export our products in more than 80 countries. So on this map, these countries are colored in blue, and to be honest, we are indeed very proud that almost the entire world is colored in blue for us. On this slide, you can see the most important and well-known instruments manufactured by Lumex Instruments. They are mercury analyzers and monitors, fluorimeters, Fourier infrared spectrometers, near-infrared analyzers, atomic absorption spectrometer, PCR analyzer, but of course on the very honorable place among these list of instruments, we have our known capillary electrophoresis system Capel. And I would like to underline that the first Capel instrument was sold already in 1997. So it means that this project exists in our company for now more than 20 years. Here you see a short list of fields, let's say application fields, where these instruments are actively used, from pharmacological industry through environmental and food industry, forensic studies, chemical industry, and up to the very complicated biotech research, including affinity studies, immunoassays, capillary gel electrophoresis in order to determine the impurities in the recombinant IgG and generally in proteins, in order to separate DNA, RNA, peptides, and also to provide capillary isoelectric focusings to separate different protein isoforms. So these are the fields. In all these fields, we suppose that the streaming potential feature can be actively used in all these fields and cases. Now, actually, we're coming to the main point of today's talk. What does streaming potential mean, where it comes from, and why it is so necessary, at least to our opinion, it is so necessary to measure, or better say, to control streaming potential. Here on this slide, we have three basic arguments and a conclusion. Classical scheme known from philosophy, permitting us to justify these conclusions. So, migration time stability is one of the most important parameters in capillary electrophoresis. C is an abbreviation for capillary electrophoresis, especially in long series of analysis. This is absolutely clear because without this stability, the software would not be able to identify peaks and thus would not be able to accurately quantify them. The second argument, the state of the inner capillary surface, or so-called zeta potential, defines the migration time stability. And this is also clear that zeta potential defines electro-osmotic flow velocity. And we know that the apparent mobility, what we see when peak comes out at the detected point, is just a sum of two mobilities, electro-osmotic flow mobility and electrophoretic mobility. Under identical electrophoretic conditions, it's clear that electrophoretic conditions remain the same. So we are very interested in providing stability in electro-osmotic flow velocity. Final argument, the inner capillary surface is typically conditioned by the long rinsing steps without any control of the results. And this is also clear. We wash the capillary, let's say we rinse the capillary with a complicated scheme of different steps like sodium hydroxide or sometimes hydrochloric acid or water or any other kind of acid or base, or sometimes with a detergent, and finally with a buffer. And we get the duration of each rinsing step simply by experiments. And we do not know whether it is enough or not, or we even do not know whether it is too much, too long. So we probably could shorten the rinsing up to 2 times or even 4 times. So this is absolutely true, this argument. As a conclusion from these arguments, we have it is necessary to have an objective control of the state of the capillary surface before each analysis. And only in this case, we will be able to say that the capillary state now is exactly the same as it was one analysis before, or probably one series of analysis before at the very beginning, thus providing the reproducibility in migration times. Let me shortly remind you about electro-osmotic flow. Everybody working in this field knows, of course, this picture. It is a classical picture which is already well known in all, even student textbooks. It's a very well-known phenomenon in CE. I will not go deeply into details explaining how it works, but rather I would like to pay your attention on the order of actions. What is done first, which step, and what comes next. So generally, EOF, electro-osmotic flow, is a bulk flow of the whole liquid inside the capillary when the high voltage is on. What we do, what is the order of actions? First, we fill the capillary with an appropriate buffer, or let's say with an appropriate electrolyte, with neutral to basic pH. Electric double layer forms at the surface, at the inner surface of the capillary, and it gives rise to EOF when the high voltage is on. This is a very roughly speaking, of course, without any details. So once again, first we have a capillary done from a few silica. We filled it with an appropriate electrolyte with, let's say, neutral to basic pH. And then we apply high voltage. Because of the presence of electro-osmotic flow, everybody knows that CE can analyze in one run both anions and cations. This is an absolute unique feature of this separation technique. Okay, let us now change the order of actions. We still have the same capillary done from pure silica. We fill the capillary with an appropriate electrolyte. Let's say the same electrolyte, it could be borate or phosphate buffer or whatever. The same electrolyte as we did on the previous slide. And thus, we facilitate the formation of the electric double layer. But then, we do not turn the high voltage on. In contrary, we apply pressure to start a bulk flow inside the capillary. And if now we manage to measure potential between the ends of the capillary, we would see that it exists, really exists, and differs from zero. This potential is called streaming potential, or shortly SP. And its existence as a phenomenon was first discovered by Quincke in 1857. So it's a known effect. The point is how to use it for the fundamental and for routine analysis in CE, commercial available CE systems. As a conclusion, once again, we fill the capillary with an appropriate electrolyte, we apply the pressure, and during the pressure, when the pressure is on, we measure streaming potential. It appears when electrolyte is pressed through a fused silica capillary. A little bit of formulas, just really a little bit. Everybody knows Helmholtz-Smoluchowski equation, which defines the dependence between the streaming potential here and zeta potential. And zeta potential, as we know, defines electro-osmotic flow velocity. A little bit of more formulas, and we come to conclusion that under identical CE conditions, electro-osmotic flow velocity is the only parameter which influences migration time reproducibility. And after this conclusion, the idea is absolutely clear. The main idea: to monitor capillary surface conditions by measuring streaming potential. So this is the main idea, and this was the starting point for our constructors and designers. Now the question is how to implement SP measurement in a commercial CE instruments. On this photo on the right, you see our last generation CE system Capel-205, in which this feature, this option was implemented. In the hardware, we constructed certain differential amplifier and several relays inside the instrument. In the software, here I will talk only shortly and briefly about this. I will come to this point in more details later. So in the software, we introduce parameter which is called exemplary streaming potential value. It is determined for the clean, absolutely new capillary and saved in the memory of the software. And then the capillary, when it is used for the routine analysis or the fundamental research analysis, the capillary is rinsed till the saved streaming potential value is finally achieved. This is the hardware, a little bit complicated, but don't be afraid of this because it is already done and it is not seen for the customers. It is inside the instrument. What is the most important thing here to underline is the presence of two contours, two circles. The first one is the high voltage. The high voltage contour is between standard high voltage electrodes, the inlet and the outlet part of this, it provides the high voltage up to 30 kilovolts, which provides the separation of the components inside the capillary. But to the same block, in the same unit, separated by the relay, we have a low voltage circuit, which defines the streaming potential and which works with the same pair of electrodes when the pressure is applied and the electrolyte is flowing through the capillary. Thus, we managed to combine two schemes in one general instrumental design. Two schemes of two different voltages, high voltage and low voltage. And let me underline that the difference between the voltages in both contours is about a million times, and we still can successfully switch between both contours. Okay? This is how it looks from the point of view of our constructors. This is the capillary cassette inside the instrument, where the capillary is packed inside the cassette and also inside the silicone tube, where the thermostating is provided by the liquid, by the water. And here you see the part of the red box, and this red box is actually what we're talking about. This is the streaming potential box. All our know-how, all our technology is hidden inside it. How the measurement goes. On this graph, you see the dependence of the streaming potential measured in millivolts upon the rinsing time. At the beginning, we have just a baseline. There is no any pressure, nothing. Then, at this certain point, we apply pressure. The signal rises up, goes up to a certain level, and stays on the plateau when the pressure is still on. Then after several seconds, at this point, pressure is off, and the signal rapidly goes down to the same level when it was before, of course, considering the certain drift of the baseline. So the difference between this upper level of the signal and the standard level, the baseline, is defined as streaming potential. Here on the right side, marked with a blue arrow, you see the SP value, measured once again as a difference between the upper level of the signal and the low level of the signal, the baseline. Of course, we met a lot of challenges when working with this scheme, when implementing this feature inside the design. And one of the challenges was to get the streaming potential value as accurate as possible, as correct as possible. Therefore, we performed thousands of such measurements in order to be absolutely sure that even after certain iterations, after certain measurements, the signal remains the same. And here you see the typical series of 5 measurements of SP under exactly the same conditions. The signal, then pressure is out, the signal rapidly drops back to the baseline, stays on the baseline, then the pressure is on, the signal goes up, makes the plateau, goes down, and you see here, if we ignore the first measurement, which is always a kind of tricky, and this is done, by the way, I say it a little bit later, it is done, by the way, automatically by the software. So if we ignore the first measurement, all 4 remaining measurements are absolutely similar to each other, and thus we do it very, very accurately. Okay? I'm sorry. So now we're coming to the more important point from the opinion, from the point of view of our customers, of the people who are working with the instrument. How we manage to implement this option in the software. We did it in several steps, and let's say a customer, an operator, does it also in several steps. First, a new capillary or used capillary, but extremely thoroughly rinsed, it's better say the new capillary is rinsed, and so-called exemplary SP value is measured and saved. It is done automatically by the software, of course. So it is saved in the memory of the software, and it is called exemplary SP value. Next step, we start routine analysis. SP is measured after the next combination of analysis and rinse, and compared, automatically compared, with the exemplary value. And then the software decides what to do according to the comparison results and a preset scheme. I would like to underline that we composed the software design as flexible as possible with a lot of options. For example, we provided the certain threshold range, maximum and minimum, and then the software decides what to do if your SP value is better than maximum, inside maximum and minimum, or worse than minimum. We can do different things, or better said, the software can do different things. For example, the software can apply another standard rinsing, I would say with buffer, for example, or two another rinsings. If, however, the value of SP measured is even worse than the minimum of the threshold, the software can either stop analysis at all, or the software can automatically apply the so-called intensive rinsing, for example, with a sodium hydroxide or with hydrochloric acid, then with water, then again with buffer, or perhaps the next time with sodium hydroxide, or perhaps to increase the time of the rinsing with sodium hydroxide or hydrochloric acid or something else, and so on and so on. So an operator is very flexible in presetting a certain scheme of reactions, what software should do if the SP value is this or that or that. And then everything is done automatically. This is the tab, the window of taken from our L4Run software package, which we normally supply with our Capel systems. And this is called measurement program. Rinse with SP control. This is the operation, the command, which can be implemented into the tab. It contains, as I mentioned, a lot of parameters, but don't be afraid of these parameters. If you wish, you can ignore most of them. What is important, however, this is whether it is measurement or determination, because thus we differ between the setting of the exemplary value, which when we use it at the beginning, when the capillary is new, and measurements of SP during the routine analysis or fundamental research analysis or anything else after the exemplary value was already measured and saved. As you see, it is the next line here. It is already, in this certain example, it was measured and saved. Then we determine when, let's say, we set threshold maximum and threshold minimum. In this certain example, it is 95% and 90%, and thus we define the range in which our measured SP value must be inside. Whether it will be inside or not, it depends upon the state of the capillary surface. And then the software decides what to do after the SP value is measured. If everything was okay, if the capillary is not contaminated, then after the final step of SP measurement, you get this very encouraged tab, very encouraged window where it is stated, information window where it is stated that rinse is successfully finished, and the value SP is, it is stated here, in this case it is 1.32 millivolts, and it says also the percentage of its exemplary value. In this certain case, it was even better than the absolutely new capillary, 101% of the exemplary value. So it means that we can continue any kind of analysis with this capillary. It is clear that the capillary state is exactly the same as it was before this certain analysis. Before I showed you how it works, here I show you what is the result, how you get at the end. This is a very typical electropherogram file after separation is done. What is not present here is the very bottom part of it, which is the standard table with the integration results. It was just cropped because of the absence of space, but it is here, of course. So we have this standard graph where we see the separation of our components. But what is not standard, not typical for CE files is what we see at the top. First, on the top level, column, this here we see how the measurements were done. This rising of the signals and falling down when the pressure is out. Here you see some statistical information. Here you see even the graph showing the statistics. And here you see the list of measured SP values. And as you see, the software automatically ignores the very first measurements, which is always, as I mentioned, which is always a little bit tricky and is not done highly accurately. But the 5 others are done, and the results are extremely similar to each other. Reproducibility and the accuracy of SP measurement under these conditions is really perfect. And the average is calculated and stated here as an average SP value after 5 measurements, 5 iterations, and thus it compares. Thus, after this, it is compared with the exemplary value, which I mentioned in my previous explanations. This is how the slide looks like. It has all the information for the people working for the fundamental research. It's a lot of information, a lot of statistical things. And also it contains the info for the people working with a routine analysis, because they know exactly that the software has determined the state of the capillary and decided after this to continue routine analysis. As you might understand, after we have implemented this feature into our instrument, we have done thousands of such measurements. But just simply have a look. On the bottom trace, which is on the red line, we have the separation of our IQ standard mix under the best conditions. So the capillary is absolutely clean, rinsed thoroughly, and the SP value is on the highest level, 84.6 millivolts. Next, the capillary was contaminated, artificially contaminated, and we got the streaming potential, which is lower. Instead of 84.6, it is 80.1 millivolts. And immediately after this, we get a shift of all the components towards longer migration time. Here, the most important shift is, of course, the first peak, because it is benzyl alcohol, as you see here on the first component. It is uncharged, and it is used here as a marker, as a label for electro-osmotic flow. Electro-osmotic flow velocity can be determined with the help of this peak. Finally, on the upper trace, we have the seriously, I would say, contaminated capillary with a significantly lower streaming potential value, 75.2 millivolts, and more pronounced shift of benzyl alcohol component peak towards longer migration time. What I would like to underline is that the shift is absolutely proportional to the decrease in streaming potential. This is very important to understand. Of course, this shift is totally different from the shift of other 2 components, because what we see is apparent mobility, which is actually a sum of 2 mobilities, electro-osmotic flow mobility and electrophoretic mobility. Therefore, there is no direct proportionality between the shift of the benzyl alcohol and, for example, phenylalphanilic acid. But studying the shift in migration times of benzyl alcohol as an EOF marker, you definitely see that there is a proportional between the shift and the decrease of streaming potential. What is important to underline as well, that even with a reversed electro-osmotic flow, it is still possible to determine streaming potential. The sign of it will be opposite if it was positive when we used it with a normal EOF. Normal EOF, as you know, comes from the inlet to the outlet when there is a minus at the detector point. At the reversed electro-osmotic flow case, the sign will be negative. And indeed, you see here that this is the standard, the baseline. Then you apply the pressure and the signal goes down, stays on the plateau, and at this point the pressure is out and the signal rapidly goes back, means rises up to the baseline, and then again, and then again. So these are the iterations, and in this certain example, which deals with the separation of some inorganic anions together with some organic acids, small organic acids like formic and acetic acids, the measurement was done, and it was clear, at this certain case at least, that the capillary is clean, rinsed, thoroughly rinsed, and the analysis can be performed further. So once again, as a conclusion, streaming potential can be used and can be controlled not only in case of standard electroosmotic flows, but also in cases of reversed electroosmotic flow. Where this can be used actually? Probably the most important questions for people who hear about this feature for the first time. I would say two groups. For the fundamental research, for the zeta potential determination, definitely. And zeta potential is extremely important, for example, to study different peak dispersions coming because of different factors. That's very important. Also for new coating design, this is important to know the SP value. Why? Because you know that when you provide chemical coating or chemical modification of the capillary from the inside, in most of cases you eliminate electroosmotic flow. But you need to have a control whether the EOF was indeed eliminated or not yet. But this is only the part of the task. The second part of the task is to know when the coating is degrading, or let's say starts degrading, because everybody knows that any kind of chemical coating from the inside of the capillary is not stable for centuries. It slowly degrades, unfortunately, and the operator does not know at a certain moment whether it has started already degrading or not yet. He gets some strange results and does not understand whether it comes from the nature of the buffer, nature of the sample, or perhaps it comes because of the degraded coating. And the measurement of EOF in this case can be a very, very valuable hint for him to understand what is happening with the capillary. Then the system peaks prediction, of course, this is very important. Electroosmotic flow and electrophoretic behavior predictions, and so on and so on. So the people working deeply in the theory of capillary electrophoresis will benefit a lot from this feature, because it is very perspective for grants, for new grants and new projects. It is, for the first time, is implemented in a CE, and clearly this is very perspectives for grants. But it is not only for the people working on the fundamental research. It is also very valuable for the routine analysis. And here on the top, as creme de la creme, I will put the first point. Save the long sequence of analysis if the capillary is contaminated after any of runs. Imagine the situation. You have programmed about 30 consecutive analyses, 30 consecutive runs, overnight. And then you went home, and the sequence has been started. And suppose also that in a sample number 5, you have some bad contaminants for the capillary. So the first 4 runs were done successfully. But after the run number 5, the capillary appeared to be severely contaminated. And the standard rinsing scheme, which you have programmed before, doesn't work anymore. It means that you have lost the analysis number 5, but also you have lost all next analysis because the capillary is still severely contaminated. In this case, if you have implemented the SP control, you would avoid such an annoying bad situation for you, because the software immediately, in this case, the software would immediately recognize that the capillary is contaminated and thus immediately apply the special rinsing scheme using very radical, let's say, very strong rinsings, very strong regions like sodium hydroxide, hydrochloric acid, can increase the rinsing with the sodium hydroxide or hydrochloric acid, and so on and so on. So in this case, all your sequence will be saved. Okay? So the next point is, of course, to improve front-run migration time reproducibility, and of course it helps you to develop new analytical protocols, because if you want to develop analysis of some new components which you never analyzed before, you need to apply also the rinsing schemes, but you do not know how intensive these rinsing schemes should be. You don't know how long these rinsing steps must be. Especially if you deal with the buffers with some additives like chiral additives or detergents additives or electro-osmotic flow additions which reverse electro-osmotic flow, and so on and so on. In this case, this feature, SP control, can help you a lot in composing, constructing the so-called effective and optimal rinsing scheme. Okay, so I finally come to the final slide, conclusions. Generally, they are, to my mind, the following. The measuring of streaming potential enables increasing run-to-run reproducibility, generally. Streaming potential allows a decrease in rinsing time if we control it. Online control of capillary surface quality before CE analysis. So this is for the first time when we implement it. We know that the capillary state, or let's say the state of the inner surface of the capillary, is exactly the same as it was before the last analysis and before the two last analysis, and so on and so on. So we keep the capillary on the same level. We keep its state on the same level. And finally, I would like to underline that the streaming potential can be measured very fast and gives information on the existing electro-osmotic flow, even when it is strongly suppressed or completely eliminated. In this case, it is 0, of course. So I think that these are the conclusions. The most important of them, there could be some more, of course, and I hope very much indeed that these findings can help you in your fundamental research or in your routine analysis. So, ladies and gentlemen, thank you very much for your attention. I am finished. Thank you.
Thank you very much, Vadim. Just a reminder to everyone, there is a Q&A button at the bottom of the screen. If you have any questions, we've got a couple that we're going to go through, but now we have time to answer those questions and go through these. So the first one, Vadim, is it possible to use SP control when performing chiral CE analysis?
Yes, of course. Sorry, probably I didn't mention it in all details. Yeah, clearly, because when you use the chiral additive to the buffer, you still have electro-osmotic flow, which means actually that zeta potential still exists. And if zeta potential exists, you can measure streaming potential. And measuring streaming potential, even when there is a chiral additive inside the buffer, you still can understand for yourself, or let's say software understand it automatically, whether the capillary was and is conditioned to a certain level which is necessary for you, or it is not yet conditioned. So you see, very interesting. Streaming potential can be used not only to determine whether the capillary is contaminated or not, it can be also used to understand whether the capillary is conditioned to the necessary extent or not. So thank you.
Perfect, thank you. The second question is it possible to measure SP in coated capillaries?
Yep, generally it is possible, of course, but we should understand that if the capillary is coated, in most of cases, the coating eliminates electro-osmotic flow. And if electro-osmotic flow does not exist, it means that zeta potential does not, it is zero, let's say, and streaming potential should be equal to zero. If the coating does not eliminate electro-osmotic flow completely, there should be a certain remaining SP value. So it is generally, it is possible.
Perfect. Another, you mentioned developing new protocols for methods with detergents. Have you worked on how to define the exemplary SP when you're using detergents as a dynamic capillary coating?
Excuse me, there was a problem in the connection. Could you please repeat the question once again? Sorry, Brad.
Of course, no problem. You mentioned developing new protocols for methods with detergents. Have you worked on how to define the exemplary SP when you're using detergents as a dynamic capillary coating?
Not yet thoroughly and intensively, but we tried once when detergent was SDS, sodium dodecyl sulfate, which is a very standard detergent to be used in, for example, micellar electrokinetic chromatography. This can be, in this case, also SP can be used because, once again, we still have electro-osmotic flow, and electro-osmotic flow, and better said, zeta potential defines streaming potential. And even if there is a detergent inside, as well as, for example, there is a chiral additive, as I mentioned in my in the last question, there is a chiral additive in the buffer. It's more or less the same situation, the same case. Electro-osmotic flow exists. It means we can measure streaming potential.
Perfect.
Okay, thank you.
Next question. In your experience, how much do you think you can reduce rinsing time?
Sometimes very significantly, because people sometimes, well, not people, me, let's say, I was working, I'm still working in this field as a method developer or whatever. I never knew how long should I rinse the capillary in order to put it in a standard, let's say, typical level of conditioning or rinsing. I simply put, let's say, 10 minutes of sodium hydroxide, or even sometimes 20 minutes of sodium hydroxide, which is a nonsense, actually, because if you deal with the analysis duration time of, let's say, 3 minutes, if you use 10 minutes only for rinsing of one step, then 2 minutes for water, then another 10 minutes or 5 minutes for buffer, and finally you analyze it just for 3-5 minutes only, then it is absolutely nonsense. 5 minutes analysis and 20 minutes of rinsing. So sometimes the rinsing can be very drastically reduced, let's say several times. Yeah.
Thank you, Vadim. Next question. The SP potential can give you an approval of the capillary condition, and the EOF should be within a percentage as far as being acceptable. But what happens when the acceptable drift of the peak times with the automatic peak ID and integration?
So, yeah. as far as I understand the question from Leo, I know it comes from. As far as I understand the question, what happens if there is a acceptable GIF of the migration time? The software normally the software should automatically identify and integrate the certain peak according to the identification. If there is already a shift, we cannot trust on the automatic integration and first of all on the automatic identification, because there might be erroneous identification if a shift has happened. With the help of the streaming potential, theoretically, we are able to recalculate the migration times of the shifted peaks, putting them in their standard, let's say, normal position. Theoretically, it is possible. But generally, the main idea of the implementation of the streaming potential is to avoid shifting of the peaks in order to avoid erroneous identification and quantification. This I would put this approach on the very first position, and the possibility of the recalculation of the shifted peaks on the second position, let's say in this priority list. Thank you.
Thank you, Vadim. And it looks like the last question. I am from an R&D lab developing new methods of CE analysis. How would your option help me?
Good question, really. If you want to determine some new components which you didn't determine before, in a new matrix which you did not analyze before, it is always a very tricky and challenging stuff. It's a lot of questions and problems associated with the method development. But one of the problems is to compose, to develop an effective and acceptable rinsing scheme between analysis in order to condition the capillary. With the help of SP measurement, you can do it much more effectively, and I would say much faster than without this feature. So this is my answer. Thank you.
Thank you, Vadim. With no other questions, I want to thank Dr. Vadim Okun and all of the audience. If you have any other questions about the webinar or capillary electrophoresis system, you can call or email a specialist using the contact information on the screen. Once again, thanks to everyone for your attention, and this concludes the webinar.
Thank you very much for all the attention. Thank you.